Hi, I'm Craig Parker, a data scientist at Planetary Health Research. While my primary focus is on climate and health research, I wanted to take a step back and share the fundamental mathematics that underlies all of machine learning. I discovered this excellent free textbook, Mathematics for Machine Learning, by Dijsselroth, Feisel, and Ong, available online at mmlbook.com. Whether you work in climate science, healthcare, or any other field, these mathematical foundations are universal, so let's dive into the journey to machine learning mastery. What if I told you that behind every recommendation you see, every prediction a machine makes, and every pattern discovered in data, there's an elegant mathematical foundation? Welcome to the journey to machine learning mastery, where we'll discover how mathematics turns raw data into powerful insights. Machine learning rests on three fundamental pillars that work together in a continuous cycle. First, we have data, our raw material represented as vectors. This data informs our model, a mathematical system that finds patterns. Finally, the learning process refines the model by optimizing its parameters. These three elements form a virtuous circle, each one strengthening the others. But before we can build models, we must learn to speak the language of data. Take something as simple as the number 8. To a machine, this isn't just a number, it's a grid of pixel intensities. We translate these abstract concepts into ordered lists of numbers called vectors. This mathematical representation is the key that unlocks machine learning's potential. If vectors are the nouns of machine learning, then matrices are the verbs. They're the mathematical operations that transform our data. A matrix can stretch, shrink, rotate, or reshape entire data sets. Watch as a simple grid of points becomes a completely different shape, all through matrix multiplication. This power to transform is what makes deep learning possible. Once we can represent and transform data, we need tools to understand it geometrically. Analytic geometry gives us the ability to measure distances between data points using the norm and to assess their similarity using the inner product. These geometric concepts turn abstract number lists into meaningful spatial relationships we can reason about. Imagine you're lost in a mountainous landscape of possible solutions, searching for the lowest valley that represents the best model. The gradient is your compass. Vector calculus teaches us that to find the lowest error, we must travel in the direction opposite to the gradient. This simple insight is the foundation of how neural networks learn. But machine learning isn't about certainty. It's about managing uncertainty intelligently. Instead of single values, we quantify our beliefs as probability distributions, clouds of possibility. This shift from deterministic thinking to probabilistic reasoning is what allows machine learning models to make decisions even when the world is noisy and unpredictable. At the heart of learning is Bayes' theorem, a mathematical framework for updating beliefs with evidence. We start with a prior belief, represented as a broad distribution. As data arrives, our posterior belief becomes sharper and more focused. This is learning in its purest form, systematically refining our understanding as we gather more information. Now we arrive at the central quest of machine learning: optimization. Imagine a complex landscape where every peak and valley represents a different model configuration. Our goal is to find the parameters that sit at the lowest point on the lost surface. This is where theory meets practice, where mathematics becomes intelligence. But how do we navigate this landscape? Through gradient descent. We start at a random point and take iterative steps in the negative gradient direction, like a ball rolling downhill. Each step brings us closer to the minimum. This elegant algorithm, repeated billions of times, is how machines learn everything, from recognizing faces to playing chess. With these mathematical foundations in place, we can tackle the four main problems of machine learning. First is regression, finding the underlying trend in data. Whether the relationship is linear or beautifully complex, regression uses our optimization tools to fit a curve that captures the pattern, allowing us to make predictions about unseen data. The second pillar is dimensionality reduction, the art of finding essence. Real-world data often lives in hundreds or thousands of dimensions, far too complex to visualize. Dimensionality reduction techniques project this high-dimensional data onto a simpler space while preserving its essential structure. What was invisible becomes visible. What was incomprehensible becomes clear. The final two pillars are density estimation and classification. Density estimation reveals the hidden structure in unlabeled data, finding natural clusters and patterns. Classification draws boundaries that separate different categories, allowing machines to recognize objects, diagnose diseases, and make decisions. Together, these four pillars encompass the vast landscape of machine learning applications. Mathematics is not just a tool for machine learning, it is the foundation that turns data into insight. From vectors and matrices to probability and optimization, each concept builds upon the last, creating a coherent framework for learning from data. Whether you're building the next generation of AI or simply trying to understand how it works, this mathematical journey is where it all begins. The four pillars of regression, dimensionality reduction, density estimation, and classification stand ready to transform data into understanding. Your journey to machine learning mastery starts here. This presentation was created using some powerful AI tools that I want to share with you. First, Notebook LM from Google helped me analyze and structure the content from the Mathematics for Machine Learning textbook. The beautiful presentation slides were generated through Notebook LM's presentation feature. For the voiceover, I used 11 Labs, an advanced text-to-speech platform that creates natural-sounding narration. These tools demonstrate how AI can democratize content creation, making it easier to share knowledge and education. If you found this helpful, please like, subscribe, and check out the book at mmlbook.com. Thanks for watching and happy learning.